Hello everyone, today we'll study probability. First of all, let me give you some review for elementary set theory. First of all, let me introduce what is a set. Set an element. A set is a collection of objects. And each object in the set is called an element of the set. The notation here is if X is an element in set S, then we say X belongs to S. Denoted by the notation X belongs to set S. Next, let me introduce subsets. Let A and B be two sets. If every element in A belongs to set B, if every element in set A belongs to set B, then we say A is a subset of B. Denoted by the notation A is a subset of B. If we use a picture, it can be represented by this. Let's set A, let's set B. Every element in set A belongs to set B. This picture has a name, it's called a Venn diagram. This picture has a name, it's called the Venn diagram. Next, let me introduce empty set. The set that contains no element is called empty set. It's called an empty set. The notation for empty set is denoted by this symbol. This symbol represents a set of empty sets. Next, let me introduce the universal set. The set which contains all elements under consideration is called the universal set. The notation for universal set is a capital S. We use capital S to represent universal set. Next, let me introduce union of sets. Let A and B be two sets. The set of all elements in A, in B, or in both the set of all elements in A, in B, or in both is called a union of set A and B. The set of all elements in A, in B, or in both is called a union of set A and B, denoted by the notation A union B. Let me show you in a picture. In a Venn diagram, assume this rectangle represents a universal set. A and B are two sets in the universe. A and B are two sets in the universe. We use two circles to represent two sets here. A union B represents all elements in A, in B, or in both. The shaded region here represents A union B. The shaded region here represents A union B. Next, let me introduce intersection of sets. Let A and B be two sets. The set of all common elements in sets A and B. The set of all common elements in A and B is called the intersection of A and B. Denoted by A intersection B. Let me show you the picture. In the picture, it looks like this. Suppose this rectangle represents a universal set. This rectangle represents universal set S. We use two circles to represent A and B. A intersection B is the common element in both sets. This is A intersection B. Next, let me introduce the complement of a set. Let S be the universal set. And let A be a set in the universe. The set of all elements in the universe but not in A is called the complement of set A. Denoted by the notation A with a C here. Or for some different textbook, they may use A prime or A bar for a complement of set A. In the picture, it looks like this. Suppose this rectangle represents a universal set. A is a set in the universe. A complement is everything outside set A, but in the universe. A complement is everything in the universe, but outside set A. This is the complement of set A. Next, let me show you the difference of two sets. The difference of two sets. Let A and B be two sets. The set of all elements in A but not in B. The set of all elements in A but not in B is called the difference of set A and B. Denoted by the notation A minus B, or for some other book they use notation A/B. They all mean the same thing. A/B or A minus B, they both mean the difference of sets A and B. In the Venn diagram, it looks like this. Suppose that's a universal set. A and B are two sets in the universe. A minus B is the set of all elements in A but not in B. Here, the shaded region here represents A minus B. The shaded region here represents A minus B. That's the set of all elements in A but not in B. Next, let me show you an example about sets. Let A be the set of 3, 5, 7. Let B be the set of X, where X is a prime. Let C be the set of X, where X is odd. So A is the set of 3, 5, 7. B is the set of all prime numbers. C is the set of all odd numbers. Here we can see that every element in A is a prime number. So set A is a subset of set B. And also, every element in set A is an odd number. So A is a subset of C. Then here we can see that A is a subset of B, because every element in set A is a prime number. And A is a subset of B, because every element in set A is an odd number. Then how about B and C? Are they subsets? How about B and C? Are they subsets of each other? In B contains all prime number. Number 2 is a prime number, but 2 is not odd. So we know set B is not a subset of C. 2 is a prime number, but 2 is not odd. So B is not a subset of C. How about C? Is C a subset of B? In set C, C contains all odd numbers, but not every odd number is prime. For example, number 9 is not prime. So C is not a subset of B, because number 9 belongs to set C, but 9 is not prime. 9 doesn't belong to B. So C is not a subset of B. Next example. Let the universal set S be the set of integers 1, 2, 3, 4, 5 up to 10, from 1 to 10. Let S be the set from 1 to 10. Let A be the set of 1, 2, 3, 4, 5. Let B be the set of 7, 8, and 9. And let C be the set of 4, 5, 6, 7. Find each of the following sets. Find each of the following sets. Let's look at the first one. What's A complement? A complement represents everything in the universe, but not in A. Here A contains numbers from 1 to 5. What's in the universe, not in A, is number 6, 7, 8, 9, 10. That's A complement. What about B complement? B complement represents everything in the universe, but not in B. So what we have here is 1, 2, 3, 4, 5, 6. 7, 8, 9 belong to set B. But 10 is not in set B. So if 10 is set B, in B complement. Then next, for C complement. C complement represents everything in the universe, but not in C. So we have 1, 2, 3, 8, 9, 10. How about A union B? A union B represents all elements in A, in B, or in both. Elements in A, in B, and in both is 1, 2, 3, 4, 5, 7, 8, 9. There's elements in A, in B, or in both. How about A intersection B? Intersection B represents the set of all common elements in set A and set B. Here, the common element in set A and set B is Nothing is common. If nothing is common, we say it's empty set. So A intersection B is empty set, since no element is common in both sets. How about A union C? A union C represents elements in A, in C, or in both. Elements in A, in C, or in both is 1, 2, 3, 4, 5, 6, and 7. That's the set of elements in A, in C, or in both sets. How about A intersection C? A intersection C is a set that contains all common elements in set A and set C. In A and C, common elements is number 4 and 5. In set A and set C, common elements is number 4 and number 5. Now, how about A minus B? A minus B represents elements in A, but not in B. A minus B represents elements in A, but not in B. Here, everything in A is not in B. So A minus B is the set of 1, 2, 3, 4, 5. Here, everything in A is not in B. This is the same as set A, but that's a special case. In general, they are not the same, but that's a special case. How about B minus A? B minus A represents a set of all elements in B, but not in A. All elements in B, but not in A. Here, elements in B, not in A. 7, 8, 9. All elements in B doesn't belong to A. So the set of A minus B is 7, 8, 9. Every element in B is not in A. Next, how about A minus C? A minus C represents all elements in A, but not in C. Elements in A, but not in C is 1, 2, 3, 4, and 5 belong to C, so remove 4 and 5. A minus C is the set of 1, 2, and 3, because 4 and 5 belong to set C, so remove 4 and 5. How about C minus A? C minus A represents elements in C, but not in A. In set C, since 4 and 5 belong to set A, we remove 4 and 5. What's left is 6 and 7. So C minus A is a set of elements 6 and 7. Next, how about B union C complement? For B union C complement, we compute B union C first. For B union C complement, we compute B union C first. The set of B union C is every element in set B, set C, or both sets. Set B, set C, or both sets is 4, 5, 6, 7, 8, 9. This is the set of B union C. This is the set of B union C. Then we take the complement. Complement is everything in the universe, but not in this set. The complement of this set represents the set of all elements in the universe, but not in this set, which is 1, 2, 3, and 10. That's B union C complement. Now next one. How about B complement intersection C complement? How about B complement intersection C complement? Let's compute these two complements first. B complement is the set of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and 10. This is the set of B complement. How about C complement? C complement is a set of 1, 2, 3, 1, 2, 3, 8, 9, 10. Then we take intersection for these two sets. Intersection represents elements common in both sets. Common element in both sets. Here what's common is 1, 2, 3 and number 10. Here what's common is 1, 2, 3 and number 10. Let B complement intersection C complement. Note, for any two sets A and B, if A intersection B is an NP set, then we say A and B are disjoint sets. In the previous example, A intersection B is an NP set. Then we say A and B are disjoint sets. Next, let me show a notation about union and intersection of sets. Let A1, A2, AN be sets. The union of the set A1, the union of the set A1 union A2 union AN can be written as union I from 1 to n of AI. Union I from 1 to n of AI. I is from 1 to n. That's A1 union A2 union A3 up to AN. And similarly for intersection, A1 intersection A2 intersection AN can be written as intersection I from 1 to n of AI. Here I is from 1 to n, that means A1 intersection A2 intersection A3 intersection AN. Next, let's try an example about this notation. What's this set? What's the intersection of I from 1 to infinity of the set from 0 to 1 over I? This is a closed interval from 0 to 1 over I. What's this set? Let's try to write out everything first. When I is 1, when I is 1, the interval is from 0 to 1. Then intersection, the next set. When I is 2, this interval is from 0 to half. When I is 3, this interval is from 0 to a third, and so on. Now, first set, from 0 to 1, that's the interval from 0 to 1. That's the first set. The second set, interval from 0 to a half. That's the interval from 0 to a half. Next one, 0 to a third. So if we keep taking intersection, what's common here? The only common element here is number 0. Number 0 is the only common element. Everything else is not common. Only number 0 is common in the set. So if I take intersection for all these sets, the only common element is number 0. So if I take intersection for all these sets, the only common element is number 0. Next, how about the union of the set I from 1 to infinity of the closed interval from 0 to 1 over I? How to find a union? Union means every element in the set. For the union, if we combine all these sets together, for the union, if I combine all these sets together, I get this set. That's the largest set. If I combine everything together, I get this set. That's the largest set. So if I combine everything together, I get an interval from 0 to 1. That's the union of the set. Next example. How about the union I from 1 to infinity of the interval from 1 over I to 1? How about this union? We can also try to list everything out. We have the union I from 1 to infinity, closed interval from 1 over I to 1. When I is 1, we have the interval from 1 to 1. This is number 1. This set only contains number 1. This is the set of number 1. Interval from 1 to 1. This set contains only number 1. When I is 2, I have the interval from half to 1. When I is 3, I have an interval from a third to 1. And so on. Let's try to write down each set individually. First set, interval from 1 to 1. This set contains only one element, only number 1. This set contains only one element, only number 1 is in the set. That's interval from half to 1. This interval contains all elements from half to 1, including the endpoint. Next one is from a third to 1. Including the endpoint. So you can see that the interval gets larger and larger. The left bound gets closer and closer to 0 as I increases. The left bound gets closer and closer to 0, but never reach 0. For unions, if I combine all these sets together, I have every all real number on the line, but not including 0, because no matter how close, it can never reach 0. So the union is the interval from 0 to 1, not including 0. If I combine all these sets together, I have a union, I have a set interval from 0 to 1, not including 0. So that's the set. That's the interval from 0 to 1, not including 0. Next, how about the intersection I from 1 to infinity? Interval 1 over I. Interval is from 1 over I to 1. Intersection means what's common, the common element in the set. Intersection represents common element in the set. Here we can see that the only common element in the set is number 1. The only common element in the set is number 1. Next, let me show you some useful formulas for sets. The S be the universal set. And let A, B, C be sets in the universe. Let A, B, C be sets in the universe. First formula, A union B is the same as B union A. And next one, A intersection B is the same as B intersection A. That means for two sets, When we're taking union or intersection, if I switch order, it makes no difference. This two formula is called the commutative law. The commutative law. Next, A union B union C is the same as A union B union C, and A intersection B intersection C is the same as A intersection B intersection C. These two formulas, they are called the associative law. That means for A union B union C, if I switch the order of operation, it makes no difference. If I do A union B first, it makes no difference. Same thing for intersection. If I switch order of operation, it makes no difference. If an operation is the same, when I switch order, it makes no difference. Let's go associative law. Next one. A union B intersection C. If the operation inside and outside the premises are different, we apply distributive law. A union B intersection C can be written as A union B. I distribute A to both of them. A union B intersection A union C. Distribute A to both of them. A union B, A union C. The operation in the premises become operation in the middle of these two sets. And similarly, if I have intersection outside, union inside, I can also apply distributive law. I get A intersection B, union A intersection C. Operation inside the premises become operation in the middle. These two formulas, they are called a distributive law. These two formulas, they are called the distributive law. Next, A union B complement can be written as A complement intersection B complement. And A intersection B complement can be written as A complement union B complement. Here, when we distribute complement into the premises, operation in the middle of the premises will be switched. Union will be intersection. Intersection will be union. These two formulas, they are called De Morgan's law. These two formulas, they are called the De Morgan's law. Next, the set A minus B can be written as A intersection B complement. A minus B represents every element in A but not in B. Same thing here. It's every element in A and every element not in B. So A minus B, the difference of two sets, can be written as A intersection B complement. Next, the complement of the universal set is NP set. The complement of the universal set is NP set. What's not in the universe is NP set, it's nothing. And similarly, the complement of NP set is the universal set. The complement of NP set is the universal set. Next, for any set, A complement is the same as set A. For any set, A complement is set A. Double negative is positive. A complement is set A. Next, A union the universal set. If I combine set A and the universal set together, I get a universal set. A union a universal set is a universal set. and A intersection the universal set. A intersection the universal set is set A. What's common in A and universal set is every element in set A. What's common in set A and a universal set is set A. Next, A union NP set. If I combine set A and NP set together, I get set A. A intersection NP set. What's common in set A and NP set is NP set, because this has nothing. So what's common in both sets is nothing. Next, A union A complement. A union A complement. If I combine set A and A complement together, that's a universal set. This represents everything in A. This set represents everything not in A. If I combine two sets together, that's everything in the universe. A intersection A complement is NP set. This set contains everything in A. This set contains everything not in A. And they have nothing in common. So their intersection is NP set. Next, let me introduce cardinality of sets. Let A be a set the number of elements in set A is called the cardinality of set A. Denoted by N of A. In some other book, they use 2 bars represent cardinality of set A. So for this class, we use N of A to represent cardinality of set A. For example, let A be the set of A, B, C, D, E. Usually use capital letter to represent sets, lowercase letter to represent elements. And let B be the set of C, D, E, F. Find the cardinality of set A, set B, A union B, and A minus B. So for cardinality of A, we count the elements in set A. In set A, we have 1, 2, 3, 4, 5, and there are 5 elements. So cardinality of set A is 5. For cardinality of B, we count the elements in set B. In set B, there are 4 elements. So the cardinality of set B is 4. How about cardinality of A union B? Let's compute A union B first. A union B is the set of all elements in A, in B, or in both, which is A, B, C, D, E, F. So the cardinality of A union B is 1, 2, 3, 4, 5, 6. Then for cardinality of A minus B, let's compute A minus B first. A minus B represent elements in set A, but not in B. Here, elements in A, not in B, is only elements A and B. C, D, E, they all belong to set B. So the set of A minus B is the set of A, B. Hence, the cardinality of A minus B is 2. There's only 2 elements. So the cardinality of A minus B is 2. So that's a review for set theory. Next, let me give you an introduction for probability. A probability is a measure of likelihood that an event will occur. A probability is a measure of likelihood that an event will occur. For this class, we'll learn probability using experiments. Let me first introduce what's an experiment. So experiment is a procedure which has non-empty sets of outcomes. And outcomes cannot be predicted. Experiment is a procedure which has a non-empty set of outcomes, and outcomes cannot be predicted. For example, when we roll a die, we don't know which number will come up, so the outcome cannot be predicted. But the set of all possible outcomes is not empty. We may get number 1, number 2, number 3, number 4, number 5, number 6. The set of all possible outcomes is not empty, but the result cannot be predicted. Another example could be flipping a coin. When we flip a coin, the outcome could be either head or tail. The outcome is not empty, but we cannot predict which side will come up. When we flip a coin, the outcome could be either head or tail, but we cannot predict which side will come up. Next, let me introduce sample space. Next, let me introduce the sample space. In an experiment, the set of all possible outcomes is called the sample space. The set of all possible outcomes is called the sample space. And each outcome is called a sample point. Each outcome is called a sample point. Let's try some example about finding sample space. Find the sample space for each of the following experiments. Find a sample space for each of the following experiments. First one, flipping a coin. What's a sample space? Sample space represents the set of all possible outcomes. When we flip a coin, the outcome could be either head or tail. So the sample space here is either the head or tail. Usually you use H to represent head, T to represent tail. When we flip a coin, the outcome is either a head or a tail. So that's the sample space. When we flip a coin, outcome could be either a head or a tail. That's the sample space. How about flipping two coins? How about flipping two coins? What are the possible outcomes? When we flip two coins, the outcome is we may get two heads. We may get a head first. We may get two heads first. We may get two heads. We may get a head first, then a tail. Or we may get a tail first, then a head. Or we may get two tails. That's an outcome when we're flipping two coins. We may get two heads. We may get a head first and a tail later. We may get a tail first, then a head. Or we may get two tails. Those are the set of all possible outcomes. That's called a sample space. How about flipping three coins? What's the sample space when we flip three coins? That's a lot. How do we list them out? Let's consider two coins first, then the last coin by itself. Let's consider the first two coins, then the third coin by itself. When we flip the first two coins, the outcome could be head, 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 tail, tail, head, or tail, tail. And when we flip the third coin, outcome could be either head or tail. Then together, if the first two coins are head and head, the third coin is also head, then the outcome is head, head, head. If the first two coins are head and tail, the last coin is head, so the outcome is head, tail, head. That's the first two, that's the last. If the first two outcome is tail, head, and the third outcome is head, then together we have tail, head, head. If the first two outcomes are tails, and the last outcome is a head, the outcome is tail, tail, head. Same thing. If the third coin is a tail, then we have head, head, tail, head, tail, 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 head, tail, 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 tail. So there are 8 outcomes. Let's put them here. This is a sample space. This is a sample space of this experiment. So the sample space here is head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. That's the simple space when we flip 3 coins. Next, consider the experiment of rolling a die. When we roll a die, And the outcome may be number 1, number 2, number 3, number 4, number 5, or number 6. So the simple space is 1, 2, 3, 4, 5, 6. Number 1 represents one dot on the face. When we roll a die, outcome could be one dot on the face, 2 dots on the face, 3 dots on the face, 4 dots on the face, 5 dots on the face, or 6 dots on the face. Usually we use number 1 represent 1 dot, number 2 represent 2 dots, 3 represent 3 dots, 4 represent 4 dots, 5 represent 5 dots, and 6 represent the face with 6 dots. So when we roll a die, the possible outcome is 1, 2, 3, 4, 5, 6. Next, how about an experiment of rolling 2 dice? What's the simple space when we roll 2 dice? So consider each die individually. Consider each die individually. What's the outcome when we roll a die? For the first die, when we roll a die, the outcome could be 1, 2, 3, 4, 5, 6. How about the second die? When we roll the second die, outcome is also 1, 2, 3, 4, 5, and 6. So if the first die is 1, second die is 1, we write 1, 1. We don't want to write 1, 1. 1, 1 looks like 11, so write 1, 1. If we write 1, 1, it looks like 11, so write 1, 1. That's a little better. To avoid confusion, don't write 1, 1. 1, 1 looks like 11. Then, if the first die is 1, second die is 2, we write 1, 2. If the first die is 1, second die is 3, we write 1, 3, and so on. We have 1, 4, 1, 5, 1, 6. That's the first row. Second row is 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Next, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So that's the outcome when we roll 2 dice. Those are all possible outcomes when we roll 2 dice. So all this together is the sample space. All this together is a simple space when we roll 2 dice. That's a simple space when we roll 2 dice. Next, let me introduce what is an event. A subset of the simple space is called event. For example, when rolling 2 dice, let E be the event of getting the same number twice. When rolling 2 dice, let E be the event of getting the same number twice. So what's event E? If we get the same number twice, that means we may get number 1 twice, that means the outcome is 1, 1. We may get number 2 twice, that means the outcome is 2, 2. We may get number 3 twice, that means the outcome is 3, 3. We may get number 4 twice, outcome is 4, 4. We make a number 5 twice, outcome is 5, 5. Or we make a number 6 twice. That's event E. E must be a subset of the sample space. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Together, that's a subset of sample space S. Next example. When flipping 3 coins, let E1 be the event of getting exactly 1 head. And let E2 be the event of getting exactly 1 tail. What's E1 and E2? Getting exactly 1 head. That means the head may be in the first place. May come from the first coin, second coin, or the third coin. So it's possible that first coin come up a head. The second one and the third one come up tails. Or it's possible that the middle one, the second one come up a head. First one and the third one come up tails. Or it's possible that the last coin come up a head. The last coin come up a head. First 2 coins come up tails. That's E1. A chance of getting exactly 1 head. E2 represents the event of getting exactly 1 tail. So the tail may come up in the first place. I'm getting heads in the second and the third coin. It's possible that the second coin come up a tail. First coin and the third coin come up heads. Or it's possible that the last coin come up a tail. First 2 coins come up heads. That's event E2. Now here we can see that E1, E2, they are both subsets of the sample space. They are both subsets of the sample space when we roll 3 coins. This is the sample space. E1, E2, they are both subsets of the sample space when we flip 3 coins. E1, E2, they are both subsets of the sample space. And here we can see that E1, E2, they are also disjoint sets. E1, E2, they are also disjoint sets. Next, let me introduce a terminology. If sets E1 and E2 are disjoint, when we consider the sets, when we consider them as events, in a sample space, then we say E1 and E2 are mutually exclusive events. if E1, E2 are disjoint sets, when we consider E1, E2 as events in a sample space, then we say E1, E2 are mutually exclusive events. They are mutually exclusive events. Now my next question is, how do we find probability of an event? In order to find probability of an event, let me first of all introduce axiom of probability first. Axioms of probability. Let S be the sample space of an experiment. And let E be an event in the sample space. The probability of event E denoted by P of E must satisfy the following three axioms. First axiom. The probability of an event is a real number between 0 and 1. The probability of an event is a real number between 0 and 1. Next, the probability of the sample space. The probability of the sample space is always 1. The third axiom. For all mutually exclusive events, E1, E2, E3, and so on. For all mutually exclusive events, probability of the union I from 1 to infinity of EI is always the same as the sum I from 1 to infinity probability of EI. Mutually exclusive event means they don't have anything in common. For these events, they don't have any common elements. And this formula, let me write it in a different way, maybe a little easier to understand. Left side can be written as probability of E1 union E2 union E3 and so on. Right side, the sum is addition. Probability of E1 plus probability of E2 plus probability of E3 and so on. That's what the left side and right side means. This means if E1, E2, E3, these events, they are disjoint events, I can write union as addition of probability of each event individually. I can write the union of probability of the union as a probability of each event as the sum of probability of each event. So probability of E1 union E2 union E3 can be written as probability of E1 plus probability of E2 plus probability of E3 and so on. That's what this formula means. That's another way to write this formula. That's the third axiom. So when we talk about probability of an event, all these three axioms must be satisfied. When we talk about probability of an event, all these three axioms must be satisfied. Next, let's prove some theorems based on those three axioms. First theorem, show that probability of empty set is 0. How do we show that probability of empty set is 0? Let's prove it. we know that empty set can be written as empty set union empty set union empty set infinitely many times. Empty set can always be written as empty set union empty set union empty set infinitely many times, and they are all disjoint sets. For empty set, they are all disjoint sets. They don't have anything in common, so they are all disjoint sets, which means they are mutually exclusive events. Then we know that probability of empty set equal to probability of empty set union empty set union empty set union so on. Since they are disjoint sets, we can also say that they are mutually exclusive events. They are mutually exclusive events. Then by axiom number 3, on the right side, I can write probability of union of sets as the sum of probability of each event. That's axiom number 3. By axiom number 3, I can write probability of empty set union empty set union empty set as probability of the first set plus probability of the second set plus the probability of the third set, since they are all disjoint sets. Then, for this equation, I can subtract both sides by probability of empty set. Subtract both sides by probability of empty set. Then on the left side, I get 0. On the right side, I get first one I get cancelled. I still get infinitely many probability of empty sets. Since each probability of empty set must be greater or equal to 0, since each probability of empty set must be non-negative, if their sum is 0, that means everyone must be 0. Since each of them is non-negative, if their sum is 0, that means everyone must be 0. So probability of empty set must be 0. Next theorem, if E1, E2, En are mutually exclusive events, then probability of E1 union E2 union En is probability of E1 plus probability of E2 plus probability of En. This looks very similar as axiom 3. Axiom 3 says probability of the union of infinitely many events is the sum of the probability of each event. And this theorem says probability of the union of finitely many mutually exclusive events is the sum of probability of each event. So the only difference is in axiom 3 there are infinitely many events. In this theorem 2 there are finitely many events here. So we try to use axiom 3 to prove this theorem. Prove it. In order to prove it, we need to find infinitely many mutually exclusive events. So here we have n events. How about the rest? Let the rest En plus 1 equal to empty set. E of n plus 2, E sub n plus 2 equal to empty set. Let everything be empty set. After En, let everything be empty set. Then E1 union E2 union En is the same as E1 union E2 union En union En plus 1 union En plus 2 and so on. Since all these are empty sets, so when I take a union, it makes no difference. So this set is the same as this set. And since the sets from E1 to En, they are disjoint sets. If I add empty sets together, they are also disjoint sets, which is called mutually exclusive events. If I add more empty sets together, they are still mutually exclusive events. Then here we can use axiom 3 probability of E1 union E2 union En is the same as probability of E1 union E2 union En union En plus 1 union En plus 2 and so on. This is the same. This set is the same as this set. Then by axiom 3, probability of infinitely many mutually exclusive events is the sum of probability of each event. Then by axiom 3, we have probability of E1 plus probability of E2 plus probability of En plus probability of En plus 1 plus probability of En plus 2 and so on. Then we know that probability of En plus 1 is NP set. This is NP set. En plus 2 is NP set. Probability of NP set is 0. By the previous theorem, probability of NP set is 0. By the previous theorem, probability of NP set is 0. Then that equal to probability of E1 plus probability of E2 plus probability of En. That complete the proof. This says probability of the union of infinitely many disjoint events is the sum of probability of each event. Now there's a corollary. If there's only two sets, if A and B are mutually exclusive events, then probability of A union B equal to probability of A plus probability of B. If there's only two sets, we can also apply this theorem. A union B equal to probability of A plus probability of B. If there's only two sets, probability of A union B is probability of A plus probability of B, if A and B are mutually exclusive events. Next theorem, let E be an event, then probability of E complement equal to probability of 1 minus probability of E. Let's prove it. We know that for any set E union E complement is always in a simple space. E union E complement is always in a simple space. That means probability of E union E complement is the same as probability of the simple space. Then we know E and E complement, they are mutually exclusive events. They don't have anything in common, so they are mutually exclusive events. For E and E complement, they are mutually exclusive events. So probability of E union E complement can be noted as probability of E plus probability of E complement by the previous corollary. By the previous corollary, probability of E union E complement, since they are mutually exclusive, I can write it as probability of E plus probability of E complement. Then they equal to probability of S. And we know that by axiom 2, probability of S is 1. by epsilon 2, probability of S is 1. So probability of E plus probability of E complement equal to 1. If I solve this equation for E complement, probability of E complement is 1 minus probability of E. That's the proof. Next theorem. Let A and B be two events. Then probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. Let's prove it. For this proof, we can use a Venn diagram to help us. Let's draw a Venn diagram first. Since this problem doesn't say A and B are mutually exclusive, we must assume they are not mutually exclusive. So A and B intersect each other. Let's set A, let's set B. The rectangle is the universal set, which is also called a sample space. Now, based on the Venn diagram, we know that set A can be written as this set plus this set. Let's call this region R1. Let's call this region R2. So set A equal to R1 union R2, where R1, R2 are mutually exclusive events. Set B can be written as R2 union R3. Let's call this R3. Set B can be written as R2 union R3, where R2, R3, they are mutually exclusive events. A union B, the entire set here, A union B can be written as R1 union R2 union R3. A union B can be written as R1 union R2 union R3. And they are also disjoint events. They are mutually exclusive events. Then we know that probability of A equal to probability of R1 plus R2 union R2. By theorem number 2, that can be written as probability of R1 plus probability of R2. Probability of B can be written as probability of R2 plus probability of R3. So union probability of R2 union R3. By theorem number 2, it can be written as probability of R1 plus probability of R2 plus probability of R3. Probability of A union B is the same as probability of R1 union R2 union R3. By theorem number 2, it can be written as probability of R1 plus probability of R2 plus probability of R3, since they are disjoint events, since they are mutually exclusive events. Then let's compute. Here, right side looks more complicated. Let's compute the right side. The right hand side is probability of A plus probability of B minus probability of A intersection B. Probability of A is probability of R1 plus probability of R2. Probability of B is probability of R2 plus probability of R3. Minus probability of A intersection B. A intersection B is the same as region 2. A intersection B is the same as region 2. So that's minus probability of R2. If I combine like terms here, R2 get cancelled, 1 over R2 get cancelled. What's left is probability of R1 plus probability of R2 plus probability of R3. And we know that probability of R1 plus probability of R2 plus probability of R3 is probability of A union B. That's the left hand side. So here we prove that the right hand side equal to the left hand side. That complete the proof. And theorem number 4 and corollary of theorem number 2. These two statements, they are called the sum rule. Theorem number 4 and the corollary of theorem number 2. These two statements, they are called the sum rule. They are called the sum rule of probability. So sum rule says probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. That's in general. And A union B equal to probability of A plus probability of B if A and B are mutually exclusive. If A and B are mutually exclusive events. That's called a sum rule of probability. The first formula is true in general. Second formula is true when A and B are mutually exclusive events. They are called a sum rule of probability. Next theorem. Let A and B be two events. If A is a subset of B, then probability of A is less or equal to probability of B. Let A and B be two events. If probability of A, if A is a subset of B, then probability of A is less or equal to probability of B. For this theorem, we can also use a Venn diagram to help us. Let's draw a Venn diagram here. A is a subset of B, so that means A must be completely inside B. Set A must be completely inside set B. Then this region here is everything in B but not in A. So the shaded region here is B minus A. The shaded region here is B minus A. That's everything in B but not in A. Then we know that set B, since A is a subset of B, set B can be written as set A union B minus A. Set B can be written as set A union B minus A. And these two sets, they are disjoint sets. So that's called mutually exclusive events. They are mutually exclusive events. Since B equal to A union B minus A, then probability of B is the same as probability of A union B minus A. Since these two sets, they are disjoint events, they are mutually exclusive events. By theorem number 2, I can write it as probability of A plus probability of B minus A. by theorem number 2, since these two sets are mutually exclusive events, I can write it as probability of A plus probability of B minus A. Then by axiom 1, probability is always greater or equal to 0. Probability of any event is always greater than or equal to 0. By axiom 1, probability of any event is always greater than or equal to 0. Then probability of B equal to probability of A plus probability of B minus A. Since this is greater or equal to 0, probability of A plus a non-negative number is larger than probability of A. Probability of A plus a non-negative number is larger than probability of A. So probability of B is greater or equal to probability of A. That means probability of A is less than probability of B. That complete the proof. Probability of B is greater than probability of A. It's the same as saying probability of A is less than probability of B. That complete the proof. Next, let's look at an example. Assume events A, B, and C have probabilities. Probability of A is a half. Probability of B is a third. Probability of C is a fourth. Furthermore, A intersection C is NP set. B intersection C is NP set. And probability of A intersection B is 1 over 6. Find each of the following probabilities. Part A, probability of A intersection B complement. Part B, probability of A intersection B complement without parentheses. Part C, probability of A union B complement. Part D, probability of A complement intersection B complement. Part E, probability of A union B union C. Let's try part A first. Probability of A intersection B complement. What should we do here? We know that by theorem 3, probability of A intersection B complement can be written as 1 minus probability of A intersection B. And what's A intersection B? In the problem, A intersection B is 1 over 6. So we plug in 1 minus 1 over 6 is 5 over 6. That's part A. Part B. What's probability of A intersection B complement? Intersection of A, probability of A intersection B complement. We can use a Venn diagram to help us. A intersection B complement. If we draw a Venn diagram, it can be written as, it looks like this. Set A and set B. A intersection B complement. That means everything in A, but not in B. This part, that's A intersection B complement. Everything in A and not in B. That's A intersection B complement. We know this can be written as probability of A take away the intersection. It can be written as probability of entire set A take away intersection B, which is probability of A is a half. A intersection B is 1 over 6. Half minus 1 over 6 is a third. That's part B. Part C. Probability of A union B complement. Again, by theorem number 3, this can be written as 1 minus probability of A union B. And what's A union B? A union B, there's a formula that says that equal to probability of A plus probability of B minus probability of A intersection B. That's the sum rule. That's called the sum rule. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. Then plug in numbers. Probability of A is a half. Probability of B is a third. Probability of A intersection B is 1/6. Half plus a third is 5/6. 5/6 minus 1/6 is 4/6. 4/6 is 2/3. 1 minus 2/3 is 1/3. Part D. Probability of A complement intersection B complement. We can use De Morgan's law here. If we use De Morgan's law, A complement intersection B complement can be written as A union B complement, which is the same as part C. This can be written as A union B complement by De Morgan's law. That's exactly the same as part C. So the answer is 1/3. Part E. Probability of A union B union C. Probability of A union B union C. There are 3 sets. Let's draw a Venn diagram first. Venn diagram for 3 sets: A, B, and C. Assume this rectangle is a sample space. We have 3 sets: A, B, and C. According to the problem, A intersection C is empty set, means A and C are disjoint sets. B intersection C is empty set, means B and C are disjoint sets. If we draw a Venn diagram, A and B, they don't touch C, so C is isolated. We have set C by itself. A and B has no intersection with set C. And A and B, since A intersection B is 1/6, that means A touch B, set A touch set B. That's the Venn diagram. That's the Venn diagram for this problem. We are looking for A union B union C. We can see that these 2 sets, they are disjoint sets. A union B and C, they are disjoint sets. So that can be written as probability of A union B plus probability of C. Since A union B and C, they are disjoint sets, I can write this as A union B, probability of A union B plus probability of C by theorem number 2. Then we know that probability of A union B is here. We found it here in the parentheses, which is 2/3. Probability of A union B, we found it here. That's 2/3. Plus probability of C. Probability of C is 1/4. 2/3 plus 1/4 is 11/12. 2/3 plus 1/4 is 11/12, and that's the answer. Next example, John is taking algebra and geometry class this semester. He estimates that the chance he will pass the algebra class is 0.90. However, he also estimates that the chance he will pass both classes or fail both classes are 0.60 and 0.04 respectively. Part A. What's the probability that John will pass his geometry class? Part B. What's the probability that John will pass his geometry class but fail his algebra class? Part C. What's the probability that John will only pass one of the class? Assume John's estimation is correct. Let's answer the question. First of all, let's set down the problem and write down what's given. Let even A represent John will pass his algebra class. Let even A represent John pass his algebra class. Let even B represent John pass his geometry class. Now let's try to write down what's given. What's given here is John estimates that the chance he will pass algebra class is 0.90. So what's given is that probability of A is 90. The chance that John pass his algebra class is 0.90. What else is given? the chance he will pass both or fail both classes are 0.60 and 0.04. If he passed both classes, means John passed his algebra class and John passed his geometry class. That's the chance that he passed both classes. John passed the algebra class and John passed the geometry class. The chance is 0.60. And the chance he failed both classes is 0.04. How do we translate this? If he failed both classes, means he doesn't pass his algebra class and he doesn't pass his geometry class. He doesn't pass his algebra class and he doesn't pass his geometry class. The chance is 0.04. That's what's given. That's what's given. Now what are we looking for here? Part A, we are looking for what's the probability that John will pass. What's the probability that John will pass his geometry class? So in part A, we are looking for probability of event B. In part A, we are looking for the chance that John will pass his geometry class. What are we looking for in part B? In part B, we are looking for the probability that John will pass his geometry class but fail his algebra class. He passed his geometry but failed his algebra. B represents he passed his geometry class and he failed his algebra. A complement means he doesn't pass his algebra class. He passed his geometry class and he doesn't pass his algebra class. That's what part B is looking for. Part C, what's the probability that John will only pass one of the classes? If John will only pass one of his classes, that means either he passed algebra and he failed geometry, or he passed the geometry and he failed algebra. Part C, what's the chance that John will only pass one of the classes? Means either he passed algebra, failed geometry, or he passed geometry and failed algebra. So what's given? That's what's given. That's what we are looking for. Let's solve the problem. In general, we must translate first, then solve the problem. Write down what's given and write down what we are looking for, then try to solve the problem. So let's use Venn diagram to help us. In general, we can use Venn diagram to help us. A and B are two sets here. That's in a sample space. Part A, we're looking for probability of event B. Based on what's given, we know that probability of A complement intersection B complement equal to 0.04. This formula looks too complicated. Can we simplify the formula, find a better formula to use? On the left side, if I apply De Morgan's law, it can be written as A union B complement. Left side can be written as A union B complement. And A union B complement can be written as probability of 1 minus probability of A union B is 0.04. If we solve this equation for A union B, I can find A union B equal to 1 minus 0.04, which is 0.96. That's A union B. And then we know that A union B can be written as probability of A plus probability of B minus probability of A intersection B. That equal to 0.96. Probability of A union B can be written as probability of A plus probability of B minus probability of A intersection B equal to 0.96. Then plug in what we know. We know probability of A. Probability of A is 0.90. We are looking for probability of B, so we don't know what it is. Let's leave it for now. Probability of A intersection B. Probability of A intersection B is 0.60. We can also plug in here. That's 0.96. Then we can solve this equation for probability of B. 0.90 minus 0.60 is 0.30. So 0.30 plus probability of B equal to 0.96. Then solve the equation for probability of B. We get 0.66. That means the chance that John will pass his geometry class is 0.66. B represents the chance that John pass his geometry class. So the chance that John will pass his geometry class is 0.66. That's part A. Part B. We are looking for probability of B intersection A complement. B intersection A complement means everything in B but not in A. Everything in B but not in A. That's B intersection A complement. That's B intersection A complement. That can be written as probability of B take away the intersection of AB. Probability of B take away the intersection of AB. So part B, probability of B intersection A complement can be written as probability of B take away probability of A intersection B. Probability of B is 0.66. Probability of A intersection B is 0.60. So plug in. The answer is 0.06. Part C. What's the probability that John will only pass one of the classes? So either he passes algebra, fail his geometry, or he passes geometry and fail his algebra. A intersection B complement is this part. It's everything in A but not in B. It's A intersection B complement. It's everything in A but not in B. This set can be written as probability of A take away A intersection B. Probability of A take away A intersection B. And B intersection A complement, the same as part B. B intersection A complement is the same as part B. That's probability of B take away A intersection B. Then plug in the numbers. Probability of A is 0.90. A intersection B is 0.60. Probability of B is 0.66. Probability of A intersection B is 0.60. Then we get 0.30 plus 0.06, which is 0.36. That's the chance that he will only pass one of the classes. Next example, let probability of A equal to 0.2 and probability of B equal to 0.4. Find the largest and the smallest possible value of probability of A union B. Part B, find the largest and the smallest possible value of probability of A intersection B. Part A, how do we find the largest and the smallest possible value for A union B? We know that A union B must be greater than each set A and set B. A union B must be greater than each part A, set A and set B. Probability of set A is 0.2. Probability of set B is 0.4. Since A union B must be greater than both 0.2 and 0.4, A union B, probability of A union B must be greater than 0.4. Probability of A union B greater than 0.4 guarantees it's greater than 0.2. Greater than 0.2 doesn't guarantee it's greater than 0.4, so we must choose a larger one. A union B must be greater than 0.4. If it's greater than 0.4, it's guaranteed it's greater than 0.2. Now on the other side, A union B is less than or equal to probability of A plus probability of B. In general, probability of A union B is less or equal to A probability of A plus probability of B. If we draw the Venn diagram, you can see that probability of A plus probability of B count the middle part twice. A union B only counted once. So A union B is less than probability of A plus probability of B. And we know that all probability, no matter how big it is always less than 1. Probability must be less than 1. Then here we know that probability of A plus probability of B is 0.6. 0.2 plus 0.4 is 0.6. So A union B must be less or equal to 0.6 and less or equal to 1. A union B must be less or equal to 0.6 and less or equal to 1. It must be less or equal to 0.6. If A union B is less or equal to 0.6, it's guaranteed A union B is less than 1. If A union B is less than 1, it doesn't guarantee that A union B is less than 0.6. So here we must choose the smaller one. On the left side, choose the larger one. On the right side, choose the smaller one. So that means A union B must be between 0.4 and 0.6. So the largest possible value of probability of A union B is 0.6. Smallest possible value of A union B is 0.04. It's 0.4. That's part A. The largest and the smallest possible value for probability of A union B. Part B. Find the largest and the smallest possible value of probability of A intersection B. In general, the value for probability of A union B and A intersection B are related. We know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. This formula can be rewritten. If I try to isolate probability of A intersection B, it can be rewritten as probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. I can bring this term to the left side and bring this term to the right side. And write probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. Then here we can see that the larger probability of A union B, A and B are constant. These two numbers are constants. The larger A union B, the smaller A intersection B. And the smaller A union B, the larger intersection B. You can see that here. The more we take away, the smaller it is. The fewer we take away, the larger it is. Because of subtraction here. The more we take away, the smaller A intersection B is. And the fewer we take away, the larger A intersection B is. So minimum, the smallest value of probability of A intersection B occurs when A union B has a maximum. The smallest value of A intersection B occurs when A union B has a maximum. And the largest value of A intersection B occurs when A union B has a minimum. The smallest value of A intersection B occurs when A union B has a maximum. The largest value of A intersection B occurs when A union B has a minimum. So for the largest possible value of probability of A intersection B, we use this formula. Probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. Probability of A is 0.2. Probability of B is 0.4. That's what's given. Probability of A is 0.2. Probability of B is 0.4. The largest possible value of probability of intersection B occurs when A union B has a minimum. The minimum for A union B is 0.4. The minimum for A union B is 0.4. So together we get 0.2. That's the largest possible value of A intersection B. Then for the smallest possible value of A intersection B, use the same formula again. Probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. Probability of A is 0.2. Probability of B is 0.4. The smallest value of A intersection B occurs when A union B has a maximum. The smallest value of A intersection B occurs when A union B has a maximum. The maximum of A union B is 0.6. So the smallest value occurs when A union B has a maximum. The largest value for A intersection B occurs when A union B has a minimum. Then 0.2 plus 0.4 minus 0.6 is 0. That's the smallest possible value for A intersection B. Next example, let probability of A equal to 0.5 and probability of B equal to 0.9. Find the largest and the smallest possible value of probability of A union B. Part B. Find the largest and the smallest possible value of A intersection B. So for part A, we know that A union B must be greater than both set A and set B. Probability of set A is 0.5. Probability of set B is 0.9. So A union B must be greater than both numbers. If A union B is greater than 0.5 and 0.9, it must be greater than larger number. Greater than 0.5, greater than 0.9 guarantees it's greater than 0.5. On the other side, A union B must be less than probability of A plus probability of B. And all probability must be less than 1. A plus B, probability of A plus probability of B is 1.4. Probability of A is 0.5, probability of B is 0.9. 0.5 plus 0.9 is 1.4. Then A union B must be less than 1.4 and it must be less than 1. Here we must choose the smaller number. If A union B is less than 1, it guarantees it's less than 1.4. So 0.9 is the smallest possible value. Number 1 is the largest possible value. Part B. Find the largest and the smallest possible value of A intersection B. Here we use the formula A union B equal to probability of A plus probability of B minus probability of A intersection B. And this formula can be rewritten as probability of A intersection B equal to probability of A plus probability of B minus probability of A union B. And we know that the maximum value of A intersection B occurs when A union B has a minimum. So for the largest possible value, we take probability of A plus probability of B minus the minimum value of A union B. That's 0.5 plus 0.9 minus the minimum value of A union B, which is 0.9. I get 0.5. That's the largest possible value of A intersection B. Then for the smallest, I plug in the maximum value for A union B. Which is 0.5 plus 0.9 minus 1. Maximum value for A union B is 1. 0.5 plus 0.9 minus 1 is 0.4. So that's the largest possible value, and that's the smallest possible value. Next, let's look at a different theorem. Let S be a set where S has S1, S2, S3 up to Sn. And let S be a sample space where probability of each sample point is the same. Probability of S1, S2, Sn. Probability of each sample point is the same. If E is an event in S, that means E is a subset of S. If E is an event in S, then probability of E is the cardinality of E over cardinality of S. Let's prove it. Since S equal to the set of S1, S2, S3, Sn, then S can be written as the set of S1 union the set of S2 union the set of S3 union the set of Sn. Here, every set is disjoint. They don't have anything in common. So they are disjoint events, or called mutually exclusive events. Since S equal to this, so I can write probability of S equal to probability of the set of S1 union the set of S2 union the set of Sn. Since they are disjoint events, since they are mutually exclusive events, by theorem number 2, I can write it as probability of the set S1 plus probability of the set S2 plus probability of the set Sn. By axiom number 2, we know that probability of S must be 1. Probability of the sample space must be 1. That's axiom number 2. By axiom number 2, probability of the sample space must be 1. Since probability of S1, S2, Sn, they are all the same, this is equal to n times probability of S1. Since they are all the same, since probability of S1, S2, Sn, they are all the same, and we have n terms here, so I can write it as n times probability of, let's say, S1. Then, if I solve the equation for probability of the set S1, I know that probability of the set S1 equal to 1 over n. If I solve the equation for probability of the set S1, I get probability of the set S1 equal to 1 over n. And since probability of every sample point is the same, we can say that probability of the set S1 equal to probability of the set S2 probability of the set S2 equal to probability of the set Sn, and that equal to 1 over n. Hence, we can say that probability of the set X equal to 1 over n for all x belong to the simple space. Probability of the set X equal to 1 over n for all x belong to the simple space. Now, let E be the set. We don't know how many elements there, so let's write E1, E2, EK. Let E be the set E1, E2 up to EK. Let E be the set of K elements. Since E is an event in S, then E is a subset of S. Since E is an event in S, then E is a subset. E is a subset of S. So E1, E2, EK, every element here belong to S. E1, E2 up to EK, every element belong to set S. Since for all x in S, probability of x is 1 over n, since I can say that probability of E1 equal to probability of E2 equal to probability of probability of EK, which is 1 over n. Since E1, E2 up to EK, they all belong to S, then for probability for each sample point must be 1 over n. Next, since E is the set E1, E2 up to EK, then E can be written as the set of E1 union the set of E2 union the set of EK, and they don't have anything in common, so they are disjoint sets. So you can say they are mutually exclusive events. They are mutually exclusive events. Every set here, they don't have anything in common. They are mutually exclusive events. Then probability of E can be written as probability of the set E1 union the set E2 union the set EK. Since they are disjoint sets, by theorem number 2, I can write it as the sum of probability of E1 plus probability of E2 plus probability of the set EK. Since probability for each sample point E is 1 over n, so we have 1 over n plus 1 over n plus 1 over n. From E1 to EK, there are k terms. From E1 to EK, there are k terms. From E1 to EK, there are k terms. So it can be written as k times 1 over n, which is k over n. Since E is the set from E1, E2 to EK, then we know that cardinality of set E is K. Since E is the set from E1 to Ek, then we know cardinality of E is K. There are K elements in set E. Since S is the set of S1, S2, go all the way to S sub n, then we know that cardinality of set S is n. So probability of E equal to K over n, where K is cardinality of set E, n is cardinality of set S. Let's complete the proof. And this formula has a name. It's called a classical probability. This formula has a name. It's called a classical probability. Let S be a sample space with finite sample points. Assume the probability for every sample point is the same. Then for all event E in S, probability of E is always cardinality of E over cardinality of the sample space, which can be written as cardinality of the sample space is the number of all possible outcomes. Because every sample point in the sample space represents an outcome. So the cardinality of the sample space is the number of all possible outcomes. Since we are looking for probability of event E, so element in E represents all favorable outcomes. So cardinality of event E is the number of favorable outcomes. Since set E is what we are looking for, so set E, elements in set E is called favorable outcome. So for cardinality of set E, we are looking for the number of all favorable outcomes. This formula is called classical probability. Probability of event E is the number of favorable outcome over the number of all possible outcomes. This formula is called the classical probability. Next, let's try to use a new formula to find the following probabilities. When a die is rolled, find each of the following probabilities. Part A, what's the probability of getting a 4? Part B, what's the probability of getting an even number? Part C, what's the probability of getting an odd prime number? So let's try to find a sample space first. When a die is rolled, the set of possible outcomes is 1, 2, 3, 4, 5, 6. That's the sample space. So part A, what's the probability of getting a 4? 4 is one of these numbers. So the probability is 1 over 6. Number of favorable outcome over number of all possible outcome. 4 is one of these numbers. So that's 1 over 6. Number of favorable outcome over number of all possible outcome. There are 6 elements in the sample space. Part B, what's the probability of getting an even number? Part B, for even numbers we have 2, 4, and 6. For even numbers, we have 2, 4, and 6. So number of feasible outcome is 3. Number of feasible outcome is 3. Number of all possible outcome is 6. There are 6 outcomes. Part C. What's the probability of getting an upright number? Prime numbers are 2, 3, and 5. Upright numbers are 3 and 5. So we have 2 of these numbers. We have 2 feasible outcomes. And the number of all possible outcomes is 6. That's the probability. In general, we need to reduce the fraction. 3 over 6 is 1 over 2. 2 over 6 is 1 over 3. And that's the final answer. Next example. When 2 dice are rolled, find each of the following probabilities. Part A. What's the probability of getting the same number? Part B. What's the probability that the sum of the outcome is 6? Part C. What's the probability that none of the dice come up 2? So let's draw the sample space first. When 2 dice are rolled, that's the sample space. When 2 dice are rolled, that's the sample space we have here. So there are totally 36 outcomes. We have 6 rows, 6 columns. There are totally 36 outcomes. Part A. What's the probability of getting the same number? If we are getting the same number, that means we are getting 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. We have 6 numbers. We have 6 outcomes here. We have 6 favorable outcomes. We have 6 favorable outcomes. And the number of all possible outcomes is 36. So the answer is 1 over 6. Part B. What's the probability that the sum of the outcome is 6? What's the probability that the sum of the outcome is 6? If the sum of the outcome is 6, we know that 1 plus 4 is 6. 2 plus 4 is 6. 3 plus 3 is 6. 4 plus 2 is 6. 5 plus 1 is 6. We have 1, 2, 3, 4, 5. We have 5 outcomes here. We have 5 favorable outcomes over 36 all possible outcomes. We have 5 favorable outcomes over 36 all possible outcomes. Part C. What's the probability that none of the dice come up 2? What's the probability that none of the dice come up 2? That means the first die cannot be 2. We cross out the second row here. First die cannot be 2. Second die cannot be 2. Cross out the second column here. First die cannot be 2. Second die cannot be 2. Cross out the second row in the second column. What's left is 5 outcomes in the first row. What's left is 5 outcomes on each row, except the second row. Nothing on the second row. For the other rows, we have 5 outcomes on each row. So 5 outcomes on each row, and there are 5 rows here. 5 times 5, there are 25. There are 25 favorable outcomes. If none of the dice come up 2, we have 25 favorable outcomes over 36 all possible outcomes. Next example. When 4 coins are flipped, find each of the following probabilities. Part A. What's the probability that only 1 head comes up? Part B. What's the probability that the same number of heads and tails come up? Part C. What's the probability that at least 2 tails come up? So let's first of all draw the sample space when we flip 4 coins. Let's draw the sample space first. For 4 coins, we can draw 2 coins at a time. For 4 coins, we can flip 2 coins at a time. For the first and the second coins, the possible outcomes are head, 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 tail, tail, head, or tail, tail. For the third and the fourth coin, the possible outcome is also head, head, tail, tail. So head, 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 tail, tail, head, or tail, tail. So we can do 2 coins at a time. If the first 2 coins are head, head, and head, and the third and the fourth coin are head and head, the outcome is head, 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 head. If the first two coins are head and head, third and fourth coin are head and tail. We have head, 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 tail. Then we have head, head, tail, head. Then we have head, head, tail, tail. Next, we have head, tail, head, 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 tail, head, tail, head, tail, tail, head, head, tail, 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 head, 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 tail, head, head, tail, tail, head, tail, head, tail, head, tail, 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 head, head, tail, tail, head, tail, 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 head, tail, 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 tail. So there are 16 possible outcomes. That's the sample space. There are 16 possible outcomes. Part A. What's the probability that only one head comes up? Only one head comes up. So we're looking for the case that only one head comes up. That's one possible outcome. Only one head comes up. That's another case that only one head comes up. One head comes up. One head comes up. So we have 4 favorable outcomes over a total of 16 possible outcomes. That's 1 over 4. We have 4 favorable outcomes over 16 possible outcomes. Part B. What's the probability that the same number of heads and tails come up? The same number of heads and tails means 2 heads and 2 tails. 2 heads and 2 tails. We have 1, 2, 3, 4, 5, 6. We have 6 favorable outcomes. 2 heads, 2 tails. We have 6 favorable outcomes over a total of 16 possible outcomes. That's 3 over A. Part C. What's the probability that at least 2 tails come up? At least 2 tails come up means we may have 2 tails, 3 tails, or 4 tails. At least 2 tails means 2 tails, 3 tails, 4 tails, or 4 tails. So for 2 tails we have 1, 2, 3, 4, 5, 6. 6 possible outcomes. For 3 tails we have 1, 2, 3, 4. We have 4 outcomes. And for 4 tails we have only 1 outcome. Together we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 favorable outcomes over a total of 16 possible outcomes. That's the answer. Next example. When a card is drawn from a standard 52 card deck, find each of the following probabilities. Part A. What's the probability of getting a club? Part B. What's the probability of getting a face card? Part C. What's the probability of getting neither a diamond nor a face card? Part D. What's the probability of getting neither a red card nor an even number face card? First of all, let's draw sample space first. When a card is drawn from a standard 52 card deck, how is the standard 52 card deck looks like? For a standard 52 card deck, there are 4 different suits. We have club, we have spade, we have heart, and we have diamond. There are 4 different suits, and we have 13 different ranks. We have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. For each suit, we have 13 different ranks. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So we have 4 different shoots and 13 different rings. There are 4 different shoots and 13 different rings. Jack, Queen, and King, they are called face card or picture cards. They are called picture card or face cards. Now let's answer the question here. Part A. What's the probability of getting a club? There are 13 clubs. There are 13 clubs. Club looks like this. Spade looks like this. Heart looks like this. Diamond looks like this. There are 13 clubs. Out of total of, there are 52 cards. So we have 13 clubs out of a total of 52 cards. That's the number of favorable outcome, and that's the number of all possible outcome. That's 1/4. Part B. What's the probability of getting a face card? We have 12 face cards. We have 12 face cards. Jack, Queen, and King. We have 12 face cards out of the total of 52 cards. That's 3/13. Next, part C. What's the probability of getting either a diamond or a face card? Either a diamond or a face card. The last row is called diamond. Last 3 columns, they are called face cards. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus 12 face cards. Don't overcount this last part. Don't overcount this part here. We have 10 cards here plus 12 face cards. They are totally 22 out of 52. There are 22 favorable outcome out of 52 all possible outcome. That's 11/26. Part D. What's the probability of getting neither a red card nor an even number card? What's the probability of getting neither a red card nor an even number card? Hearts and diamond are red. Heart or diamond, heart and diamond are red. So since we're getting neither a red card, we cross out heart, cross out diamond. Cross out heart, cross out diamond. We have 2 rows left. If we cross out heart, cross out diamond, we have 2 rows left. And no an even number, no an even number card. So cross out even number cards. Number 2 is even, cross out. 4 is even, cross out. 6 is even, cross out. 8 is even, cross out. 10 is even, cross out. What's left is 1, 2, 3, 4, 5, 6, 7, 8. We have 8 columns left. 2 rows, 8 columns. We have 16 favorable outcomes over a total of 52 cards. We have 16 favorable outcomes over a total of 52 cards. 16/52 can be reduced as 4/13. And that's the answer.